Hello everyone. Now we have to discuss electrical equivalent of coupled circuits. So this is what one of the connection in this C. The dot conventions are provided in coil 1 as well as in coil 2, right? This is, let us say, so we are providing the electrical equivalent of coupled circuit. Let us say this is coupled circuit. So let us consider a coupled circuit. This is the coupled circuit. In this, what we are having, see, between these two coils we are having the mutual inductance. Is it positive M or negative M? It is positive M. Why it is positive M? See, from the both the loops, the coils, the current enters the dot, right? We can write that point. Where M is nothing but positive, because for the loops in both the coils, the current enters the dot. That is the reason, right? So from both the coils, the current enters the dot. Obviously we have positive value of mutual inductance. Clear? Then this is first observation. Next observation is what? So this is the self inductance of coil 1. This is self inductance of coil 2, L1, L2, right? Like that. This M is what? Mutual inductance between these two coils. Let us say M into di1 by dt and M into di2 by dt. Have to write that points. L1 into di1 by dt, like that. L2 into di2 by dt, and M into, with respect to current 1 in loop 1, with respect to rate of change of current in loop 2. That's it, right? Because M is present between two coils. So from this is what? Which is nothing but voltage drops, right? Voltage drops in loop 1. This is what? Voltage drop in loop 2. But coming to this is also what? Mutual inductance into di1 by dt. This is also voltage drop with respect to coil 1. This is what? Voltage drop with respect to coil 2. Why it is coil 2? Because see, the rate of change of current in coil 2, like that the rate of change of current in coil 1. So this is about the introduction of this coupled circuit. Now we have to get the electrical equivalent of this coupled circuit. So this is the electrical equivalent of coupled circuit. This is the electrical equivalent of the previous coupled circuit. See, in this what we are having? Self inductance L1 into di1 by dt, L2 into di2 by dt, M into di2 by dt, M into di1 by dt. Because M is what? Mutual inductance between coil 1 and coil 2. That is, represented with what? Dependent source, because the voltage in either circuits, from this circuit or this circuit, the voltage in either circuit may controlled by current in each coil. See, in this we have to get the mutual inductance di1 by dt. The voltage in this coil is controlled by current in the first coil. Like that, the voltage in this coil is controlled by current in the other coil. Therefore, we can represent this with voltage, current controlled voltage source, right? So in this, we can first get the analysis with respect to time domain voltage drops. Okay, then apply KVL based upon the current direction. Apply KVL, we will get from first loop V1 of t, which is equals to what? L1 into di1 by dt, or di1 of t, plus like that L2 into di2 of by dt, right? Like that, from loop 2 we can get, sorry, here mutual inductance, right? This is what? I2 only. See, from this loop L1 di1 by dt completed, m into di2 by dt, this is m. Like that, from this loop to L2 into di2 of t by dt plus m into di1 of t by dt completed. These are the time domain voltage equations. Like that, we will get frequency domain voltage equations. This is about what? Electrical equivalent circuit. But this case is what with respect to time domain analysis. This case is what with respect to frequency domain analysis. This is what? Frequency domain analysis. That's it. We all know that to change from time domain to frequency domain, t by dt, which is equals to what? J omega. That's it, right? So from this you can write V1 of t, which is equals to what? L1 into di1 of t by dt plus m into di2 of t by dt. Just substitute d by dt is nothing but j omega. Therefore, this is what? V, which is equals to, or you can write V1. Okay, this is L1. D by dt is nothing but j omega. In place of I of t, you have to write I1. Like that, plus m j omega, you have to write I2. That's it. We are having this equation, right? L1 into j omega I1 plus m into j omega I2. Similarly, for V2, which is nothing but what? L2 j omega I1, sorry, L2 j omega I2, right? The current through this loop 2. Like that, m into j omega, the current through loop 1. That's it. This is about the loop equations from time domain analysis as well as frequency domain analysis, and these are the representations of electrical equivalent of coupled circuits. This is in frequency domain. Like that, this is what in time domain. Just we have to differentiate the circuits. Okay, this is frequency domain and that one is what? Time domain. Now here I am providing the different coupled circuits. This is time domain analysis, this is frequency domain, right? This is given coupled circuit. For that we can provide time domain analysis equivalent electrical equivalent circuit. Like that, frequency domain electrical equivalent circuit. See, in this the dot is what? Like this. In the left hand coil, current comes out of the dot, while in the right hand coil the current enters the coil through the dot end. Hence M turns would be negative, right? Because from this end the current what? Enters. From this end the current leaves. Sorry, in this end the current leaves, in this end the current enters. Therefore obviously M is negative. If the current enters from the both the ends, if it is then we can say that is positive M. If the current leaves from one end as well as the current enters from one end, we can say that M should be negative. Okay, so this is the analysis of time domain from this coupled circuit, like that frequency domain. See, that's why we are having negative M, negative M. Clear? Negative. Sorry, this is what? Yeah, here we can provide negative value here, negative value here. Next circuit, see, in this case in both the coils the currents are coming out of the dot ends. Therefore from this circuit the current is coming out of the dot. Clear? From this circuit the current is coming out of the dot. Then we can say we have positive M. Therefore we are having plus M, right? Plus. This is with respect to frequency domain, this is with respect to time domain. Clear? Then this is a different case. See, in this case the current enters from both the dots. See, from this coil 1 the current enters from the dot, from this coil the current enters from the dot. Therefore we can assume that M is said to be positive. But see the current direction, the current direction of the second coil reverses. Therefore we can say that M is said to be negative value. M is said to be negative value. So we can say that we have to observe the dot convention as well as the current direction. Then only we can obtain the voltage drops with respect to time domain analysis as well as frequency domain analysis. See, here the current is what? As it is. But see, the current is given direction is what? Right to left. So left to right. So we can consider right to left direction. That's why it is said to be minus I2. Therefore M is said to be minus M. M is said to be, here also see, here we have minus M, right? Next circuit, see, here the current direction of coil 1 changes, but the dot convention place is same, right? The current enters from the both the coils. Therefore M is said to be positive, but the given coil 1 current direction is what? Negative value. Therefore we can say that M is negative, or we can say plus M. But to write that voltage loop equation like this, we have to write V1 is equals to minus L1 dI1 by dt, like that you have to write. Okay, so this is about the different circuit topologies with respect to time domain as well as frequency domain. So in this circuit the current enters from the both the dots, but he provided the polarity of the supply voltage changes. See, here the polarity of supply voltage is changes. Here it is minus, here it is plus, right? Obviously we will get the different loop equation. That's why we are having what? Minus V1, but we are having positive M only. We are having positive M only, but coming to V1, so to get positive V1 we can write minus L1 dI1 by dt minus M dI2 by dt, which in turn what? Which in turn represents what? Negative mutual inductance only, right? Then you have to be very careful about the dot conventions as well as the current direction as well as the polarity of supply voltage, right? See, in this circuit the current direction is same, but see, here it is minus, it is plus. Polarity of supply voltage changes. That's it. So these are all very important observations from different coupled circuits. So from this we can write one point. Here I can provide one important point. We have to very careful about dot convention, right? Next, current direction and polarity of supply voltage. First we have to cross check the dot conventions, later current directions and polarity of supply voltage. You have to be very careful. This is about the importance of dot conventions and application of dot convention in electrical equivalent coupled circuits.